This session is going to address the Math 31, the trigonometry section. The first comment I have has to do with proving identities. Now this is a repeat, shall we say, from Math 30-1. And again, depending on your teacher and how particular they were, you may know all of this and you may not know all of this. So I'm kind of particular about proving identities. If I'm asked to prove something, and I'll just make something up, I'm not going to say that this works, but actually I do know that this one will work. But if I'm asked to prove that, then what I want to see for formatting is a line down the middle. You do all sorts of work here. You do all sorts of work here. And when you prove that both sides are equal, then you can put an equal sign and you can write proof complete and whatever else. Be goofy and we can put a happy face in there or whatever. But during this section here, I don't want to see equal signs. So don't use equal signs as you're going through, as you're doing them. If you want to do bullet form or something down the side, we have to be really cautious about no equals. Now, if that worries you, the other way you can do it is you can write the letters LS, and then you can do all of your work here for LS, and then go vertically. And then if there's any work you have to do for the right side, then you can go and do all the work for the right side. Okay, so in terms of formatting, just be cautious. If you're not sure, reach out and ask me. And then in terms of the actual process of identity proving, again, it was gone over in 30-1, but it might be a reasonable thing to just kind of highlight some of the big ideas when you're proving identities, because there's no real right way to do them. But some strategies for doing some proofs. One strategy is to work on the more complicated side. Another suggestion that works really well most of the time is to change to sine and cos. If you look at your formula sheet, you'll notice that a lot of the identities have sine or cos kind of interspersed in there. So sometimes that's a really good way. Other things just to note is you might have to factor. That's kind of just a procedural type thing. You might have to do common denominator work. Again, that's just sort of procedural, but it might come up. And I don't think we get into this a lot, but sometimes you have to multiply the top and the bottom by a conjugate. And if you run into one like that, certainly reach out and ask me. So those are some ideas. These are the two that I mostly employ. And then, you know, these do come up as the question kind of shakes out. Okay, so those are some ideas about trig identities. I feel like most don't need a ton of help there, so I just want to do a little brief overview. I wanted to spend a bit of time, question 2, on some trig equations. Again, overview from, or a kind of a spillover from 30-1 again, but we didn't do as many in 30-1 with double or triple angle type questions. So I thought it might be worthwhile to give you some ideas as to how to go about doing these and some good processes in place. Again, I don't think they're super difficult because it is a bit of a repeat, but this one is the one that I thought we might do. So 2 cos of 2x is equal to root 3, and they give the domain is 0 is less than or equal to x is less than or equal to 2 pi. Okay, now the first thing I do, and again, you can proceed a little bit differently, but I always have kind of my eye on the question. I go, oh, I've got a 2x in the question when my domain is actually only telling me about x. So I'm immediately going to keep in mind that I'm going to double everything. I'm multiplying each of these by 2, and that my answers for 2x have to go from 0 to 4 pi. I'm just going to kind of keep that in the back of my mind. Okay, now we're going to go and we're going to try to work through this question. So the first step in this question would be to divide both sides by 2 So we get cos of 2x equals root 3 over 2. Now, when I chat with students about how to solve these, I'm a person that really likes to deal with degrees and then change to radians. I had feedback that a lot of students are just totally cool with radians, which is great. And I have provided a unit circle. I'm so kind in Math 31. So you have the unit circle. So we can certainly write our answers out in radians. Just be cautious. If you like to work in degrees, you always have a little peek back. And if the original domain was given in radians, then your final answers have to be in radians. So just be mindful of that. So when we think of the unit circle and where cosine is positive root 3 over 2, look at your unit circle, find where the first coordinate is root 3 over 2. You will find that in one rotation, the answers that have that occurring are pi over 6 and 11 pi over 6. Okay, that's for one full rotation around. However, because we've got this little 2 here and we had changed our domain here to say basically go around twice, we have to add 2 pi to this. Now adding 2 pi, if you make a common denominator, is like adding 12 pi over 6 to this answer. So it creates a second answer of 13 pi over 6. And then we do the same thing with this one. We add 2 pi to this, which is again like adding 12 pi over 6 doing the common denominator. So that will give us 23 pi over 6. So now we've got answers that range from 0 to 4 pi. So we're ready to roll and get our final answers. And what we do is we just divide by 2 to get our final answers. Now dividing by 2 is like multiplying the bottom by 2, right? Multiplying by a fraction. So these will turn into the answers pi over 12, 11 pi over 12, 13 pi over 12, and 23 pi over 12. And we can put it in a nice little set if we want to, something like that. Now, some of the questions in the module do ask for general solutions. And so if we want to change these into general solutions, let's just say this is question 1A or 2A, I'm sorry. And the second one is the same thing, write the gen, but we're going to ask to write the general solution. What we do is we go back to the first answers, because remember our second answers were generated by going around another full circle. And so the general solutions then would be pi over 12 plus 2 pi n is an integer. And what this says to the reader is that you're going to get to pi over 12 and then you're going to go full rotation one way forever or the other way. And the integers just mean that you're doing it 1 time, 2 times, 3 times, positively or negatively. So this is one part of our general solution. And then the other part of our general solution is we take the 11 pi over 12 and we do the exact same thing like that. Okay, so this particular question I hadn't started with general solution, but I thought it was kind of worthwhile to throw it in there because that is an expectation that you'll be able to write general solutions as well. Okay, so question number 3 that I thought was important to cover. This is like 1B in section 3. So if you've been toiling away in module 4 in the trig sections of limits and derivatives, etc., you will see that there are some limits that they give you, they prove them to you, and then they want you to apply them and use them. And so this is one that is a little bit of an odd duck, shall we say. So we're going to do one similar. So it's going to say the limit as theta goes to 0 of sine of 6 theta over 7 theta. Okay, now there is a limit. If you look through your formula sheet, you may kind of spy something that looks similar, and there is a limit on there as theta goes to 0, and it's sine theta over theta. Okay, and when you get that particular thing to come popping out at you, the answer to that is 1, and you'll find that on your formula sheet. Okay, so just kind of, browse around, have a look at that. So we sort of have a bit of an eye on the prize. We have a problem here with the fact that we have a 6 theta on the top and a 7 theta on the bottom. And I have seen students say, well, heck, I'm just going to common factor the 6 out and then common factor the 7 out and get it ready to go. It actually leads to a right answer, but for very wrong reasons. 6 theta is an angle. If I said to you that we had, the sine of, let's see, 6 times 30, the right way to do that would be the sine of 180. It would not be 6 times the sine of 30. This would not give us the right answer. So we cannot just common factor the 6 out. We have to be a little craftier, shall we say, about doing it here. So what we're going to do is, here's how we're going to be crafty. We're going to multiply the top and the bottom by 6. We're going to kind of manipulate it, okay, into looking like we want it to look. So it's going to be the limit as theta goes to 0 of sine of 6 theta. And let's see how I want to write this, times 6. We'll just write it this way. I'm just going to put it out front, but it's okay. And then 7 theta, like that, times 6. Okay. Now we're going to reorganize a little bit. Okay. So next step is the limit as theta goes to 0. And we're going to reorganize these guys together and then the other guys together. So I'm just changing the order. So we get sine of 6 theta over 6 times 6 over, did I do that right? Yep. Okay, like that. All right. And then, oh, no, just a minute. I know what I didn't do here, right? I want the theta, because everything's multiplied together. I'm going to throw the theta over here. Okay, it's going to go on with that 6. There, that's better, because we have to have a theta top and bottom. Now, the one thing you might be looking at and saying, this does not match up with the 6 theta. However, think about it. When the limit theta is going to 0, it's the same value as the limit of 6 theta going to 0. Because 6 times 0 is 0. So then we can rewrite this as the limit as 6 theta goes to 0 of sine of 6 theta over 6 theta multiplied by 6/7. Then we can apply the limit. This entire limit then becomes 1 multiplied by 6/7. Our answer is 6/7. Okay, so kind of just a bit of manipulation there, and then this realization that if we're doing the limit as theta goes to 0, it's exactly the same limit as 6 theta going to 0. You tuck the 6 in the front, you now have a limit that matches up with one of the limit statements that you have on your formula sheet, and you rock and roll and you're good to go. Okay. All right. Yeah, onwards and upwards. Here's a little comment. If you may have seen this one, number 8. Just want to talk about them really briefly. On the final assignment, it's a little bit odd to know what it says on the right hand side. The right side says this, tan of xy. Please know that that means the tan of x times y. The y is not part of the angle. If they wanted it to be part of the angle, this would be in brackets. Okay, don't misinterpret that. I had chatted about it when we had our Zoom session, so I thought I would throw it in there. All right, now, oh, and there's a typographical error on number 7 too. What was the typographical error? Let me go and just find the typo. I think it had an X and it's supposed to have an H or something. So let me just go pull that up for us. Number 7. Yeah, it says the limit as H goes to pi over 4. That should be X. So it says the limit as H goes to pi over 4. Oops. It's the limit as X goes to pi over 4. Okay, so you may have just picked up on the fact that an H isn't even in the question, so it'd have to be an X. Okay, dokie. Now let's do a harder derivative, a bit of a harder derivative. This section is not too bad, this whole module particularly, because you've had lots of work in Trig in Math 3-1. And then in module 3, we did all sorts of derivatives. And so it's kind of putting all the pieces together. Now, having said that, they can get kind of difficult. So let's try this guy. Find the derivative of y equals the square root of cosecant of 2x. Okay, so we have to be really careful here that we are going to have to apply the chain rule a number of times. Okay, so this is a chain rule on steroids, so to speak. So we're going to have to apply it to the square root part. Then we're going to have to worry about applying it, doing, and that should say cosecant. That my writing is not super good there, sorry. Then we're going to have to apply it to the cosecant part. And then we're going to have to worry about doing the chain rule for the double angle of 2x. Okay, so we've got to kind of keep our head about us as we go about doing this. So I would start by rewriting the question as cosecant of 2x bracket to the half power. Okay, now here we go. So we're doing the derivative of the outside, just the normal power rule. So the 1/2 drops down, cosecant x 2x to the minus 1/2. That's just the normal power rule. Half down, subtract by 1. Now we have to do the derivative of cosecant. Now you're not asked to memorize these or anything. So I'll just do this in steps. So now we're doing d dx of cosecant of 2x. So just grab your formula sheet out and look down for what the derivative of cosecant is. So we're going to carry this along. Now we're doing the derivative of cosecant. Again, I don't usually memorize these. I look them up as well. So it's minus cosecant of 2x, cotan of 2x. And then we have to multiply by the derivative of the 2x because we're kind of going from outside, inside, right? So the next step is 1/2, y prime, cosecant 2x to the minus 1/2. And then this is just copied down again. And then the derivative with respect to x of 2x is just times by 2. And then it's just a little bit of reorganizing and trying to make the final answer look a little bit better. You can see that this 1/2 and this 2 will cancel each other out. So let's do that. And then I'm going to do a little bit of reorganizing with our answer to try to combine a few things because we have a couple of cosecant 2x terms. So let's see how this would look. So we would have minus cosecant 2x. I'll put those in brackets, times by cotan of 2x. And then I'm going to drop this term down to the bottom as cosecant of 2x to the half power. Okay, I don't know that we had to do that, but I might make it easier. Now look at this. This has an exponent. If I was to put this in brackets, this would be an exponent of 1, right? These are identical terms with different exponents. So what we could do is we could subtract the exponents. Okay, so we get 1, take away a 1/2 is a 1/2. And so we would then have minus cosecant of 2x all to the half power on top times by cotan of 2x. That's a good answer. I don't mind that. However, you might want to change it back to a square root just because the first actual question had a square root in it. That's neither here nor there, but there would be a final reduced answer. Okay. So again, just kind of recapping this. We had to do the derivative of the outside, and then the derivative of the cosecant, then the derivative of the 2x, and then kind of mess around and tidy it up, so to speak, to get our final answer. Okay, so hopefully those questions are a helpful overview of Module 4, the trigonometry section in the calculus.